Good afternoon, everyone. My name is Karel Ortiz, and I would like to introduce the members of this team. They are Mariano Vega, Fernando Rojas, Gisela Armenta, Matilde Baeza, and Elizabeth Hilario. Now I will start by describing the problem. The problem says that in a hydroelectric generating plant, 100 cubic meters per second of water flows from an elevation of 120 meters to a turbine, where electrical power is generated. It is determined that the total irreversible loss of load in the pipe system is 35 meters. Then, if the total efficiency of the turbo generator is 80%, estimate the electrical power output.
The resolution strategy chosen for this problem was based on exercises done in class. From the diagram, we determine the points of interest according to the results we need to obtain, and then we propose an energy balance. As it can be seen in the diagram, points 1 and 2 are exposed to the atmosphere, allowing us to get rid of the pressure difference in the energy balance. Likewise, we can eliminate the velocity term on both points, as these are negligible due to the really slow and barely noticeable change that the water level will have in both points. And finally, we set the elevation of point 2 as 0, so that the elevation of point 1 in relation to point 2 is now the difference between these 2 points.
For the resolution of this exercise, we need some values. So thanks to the data that the problem gives us, we know that the volumetric flow is 100 cubic meters per second, and the height from point 2 to point 1 is 120 meters. So we take C1 as 120 meters. We also know that the total irreversible loss of load in the pipe system is 35 meters, and the total efficiency of the turbo generator is 80%. We take the density of the water as 1000 kilograms per cubic meters, and since point 1 and point 2 are exposed to the atmosphere, we take pressure 1 and pressure 2 as atmospheric pressure.
To begin with the resolution of the problem, first, the mass flow of the water that passed through the turbine have to be calculated, and it is a product of the density and the volumetric flow. The mass flow has a value of 100,000 kilograms per second. Subsequently, the energy equation is modified because point 2 is taken as a reference level, that is C2, and it is equal to 0. On another hand, points 1 and 2 are open to the atmosphere, so pressures 1 and 2 are atmospheric pressure, and the flow velocity is negligible at both points. Therefore, V1 and V2 are equal to 0. The energy equation for the stationary and incompressible flow, solving it to find the hydrostatic head of turbine, turns out to be the subtraction of C2 and the loss of head, so that the turbine head turns out to be 85 meters.
Now that the load extracted by the turbine has been calculated, we calculate the power generated by a total efficient turbine, where turbine power is equal to mass flow multiplied by gravity force multiplied by the load extracted by the turbine. The result is 83,400 kilowatts generated. But because the turbine is not 100% efficient, we calculate the real power generated by this specific turbine, where electric power is equal to turbo-generated efficiency times turbine power. The result is 66,700 kilowatts actually generated.
Hi, my name is Elizabeth, and I'm going to talk about the results from ABET. It is required to generate hydroelectric power, making the pertinent calculations a turbine power of 83,400 kilowatts was obtained. This means that an ideal turbo generator would generate 83,400 kilowatts of electricity from this research. However, the electrical power generated by the actual unit is 66.7 megawatts. Power generation would increase by almost 1 megawatt for every point improvement in the efficiency of the turbo generator unit.
My experience collaborating with my classmates was very pleasant because we all work equally as a team. contributing ideas and supporting each other. In this occasion, the team was randomly formed by the teacher, and due to the current situation of the pandemic, we did not have the pleasure of knowing each other. However, that was not an impediment to work hard together and perform quality work.
When making the project, it was a bit challenging collaborating with my teammates, especially due to not being able to see each other directly and having to organize and rely completely on technology for everything. Either way, it was very satisfying as everyone came through, and there weren't many complications at all when working as a team. Teams were made randomly, and we didn't know each other, but still, we managed to make a quality project, and we had no problems in organizing each other and delivering our parts.
Teamwork on this project was a great experience. We all did our part to make the project look as good as possible, and although the current circumstances are not the best, I think we agreed and did our best to achieve a quality work.
I think this is the first time that the whole team did their own part to do this project quickly and efficiently. I had no problems with any member. There was good communication between the whole team, and everyone agreed on the decisions that were made. It was a good experience for me to be able to work with my classmates despite the current situation.
Teamwork was super easy and organized. We all agreed in the election of the problem and its resolution. Everyone knew what to do and delivered the work on time so that it could be checked before deadline. All questions were answered and everyone were up to collaborate with any doubt. The contribution of all made the work light and fast, of course with the priority of delivering quality work. I personally enjoyed working with this team.
Teamwork was easy despite of the new ways of taking classes because we were always in communication and we shared the roles to be able to develop the project correctly. We realized that you can do a good job and be a good team if you want.